All right, linear motion, chapter 2. Well, it may be chapter 2 in your book. Depends on which book I'm using for this course. But linear motion is what we're going to start out with here. And to talk about motion, we're going to talk about how motion is relative to something else. Right now, if I had a student in my lecture and they were sitting in a chair, I might ask them how fast they were going, and they could answer 0 and they'd be correct. But they could also give their speed around the sun at 30 kilometers per second, and that would also be correct. So how could they be moving 30 and 0 at the same time? Well, it's because motion is relative to some frame of reference. And so if you're talking about your chair, your speed is 0. If you're talking about going around the Earth or the Earth going around the sun, that's a different matter. If you're talking about the solar system going around the center of the galaxy, yet another frame of reference. So motion is always relative to something else. If they don't say in the book, they're talking about relative to the Earth. Vectors versus scalars. Some numbers just have a size. That's called a scalar. Scalars are quantities that have a magnitude. So the book might say magnitude. Don't let that throw you off. It's just talking about the size of the number. So 146 meters or 12 elephants or something like that. Scalars are added just like normal numbers, like you're familiar with in mathematics. But vectors are quantities which have a magnitude and direction. 12 meters to the right or 32 meters per hour, miles per hour east. Those cannot be added like scalars. We need a certain type of vector addition or subtraction to deal with those, and that's in a different video. So if we're describing how far that we've gone, we could use the word distance, and that would be a scalar quantity. Standard units for distance would be meters or feet or miles, the things you're familiar with. As you measure how far you've moved with respect to you, like a pedometer would read, that's what we're talking about when we're talking about distance. In physics, there's another word that's a little bit more nuanced than distance, and we call it displacement. And displacement is a vector quantity. So it depends on how far you've gone relative to where you started. The units are just the same as distance. They're meters, feet, miles, all those things. But the difference is you have to measure it with respect to where you started. So let's look at an example. So we have this point P, and we go 4 meters, and then we go 2 meters, and then we go 4 meters, and then we go down 2 meters. Well, if we're talking about the person walking and we want to know how far they went, their distance, it's going to be 12 meters. However, more disappointingly, if we talked about their displacement, the displacement is 0 if they end up where they started, which sounds like you haven't done any work, but you know, that's what displacement is. The book will often, many books, different books, have different ways of labeling these things. Vx in a book would stand for velocity in the x direction. You'll see VO or V naught, it's pronounced. Sometimes that would be your starting velocity in the x direction. I usually, when I'm solving these problems, just use VF, not the VX that they use in some textbooks. I'm usually going to use VI for your initial or your starting velocity, not VOX. I usually use distance instead of the X or the Y or the Z, whatever we're doing. Okay, so if we're going to measure how fast we're going, we're talking about speed, your rate of change of distance, right? Well, speed is a scalar quantity, and standard units are meters per second. Down here in this little equation, I have V equals distance, V average, the line over there means average, distance over time, D over T. Well, if we're talking about velocity, it's basically the same, but velocity is a vector quantity, so we have to have that direction associated with it. Our units are going to be the same, meters per second usually, or miles per hour, or something like that. The formula is going to be the same. The difference comes when we start adding our vectors, and we'll talk about that in another video, and we'll look at that more a little bit later. In this particular video, we're going to say that everything's in the same direction in the x-plane, so it'll make it really easy for learning this at first. So back to our square here, if our person went 4, 2, 4, 2, that means that they went 12, and if it took them 4 seconds to do that, well, then they were going 3 meters per second for a speed. But if we wanted their average velocity, they didn't go anywhere. Their distance would be 0. So what we would end up with would be their velocity would be 0, which seems a little bit misleading. And that's why we have to know the difference between what these words are actually meaning, and we need to use the words appropriately and understand there's some nuance in some of these things. For every day, just kind of talking to somebody, yeah, you're not going to get that technical. But here in the book, it does matter. So here are some symbols that we need to know. This triangle-looking thing is a Greek letter delta, and it just means change in. So when we see delta V, that means take the final minus the initial. Likely have seen these things before. V with a subscript I is how I'm going to denote initial velocity, the velocity at the start. V with an F will be final velocity, D is displacement, A is acceleration. And if we know what the units are that we've measured all these things in, when we're looking at a story problem, it'll be easier for us to say, oh, well, that's an acceleration. Oh, they're talking about a velocity here, when we know that these are the units for these particular symbols. So let's look at a practice problem here. We've got a boy taking a road trip to Pittsburgh. Let's see how we can solve that. As we do this problem, I'm going to think out loud to kind of show you what my thought process is for solving physics problems. So a boy takes a road trip from Philadelphia to Pittsburgh, and the distance between the two cities is 300 kilometers. Well, I'm going to write that down. That sounds like a good thing to write down. D equals 300 km. Don't forget to label stuff. He travels first at 100 kilometers per hour at a speed of 35 meters per second, and then last 200 kilometers at 40 meters per second. What's his average speed? Well, let's see, we have two different distances then. So I'm going to call this distance total. I'll just put a little subscript t there so I know that this d is the 300. The first leg of the trip, I'll call it d1, is 100 kilometers. Okay, and then it says the second leg of the trip, well, first it says the speed was 35 meters per second, or the velocity. It's a velocity because we know what direction it is. 35 meters per second, and that's V1. Let's see, D2 was 200 kilometers, and V2 is 40 meters per second. And they want to know what the speed was, the average speed. So I'll just put it like that. That means the average velocity total equals question mark. And I'm going to leave that there so my instructor knows that's what I'm trying to solve for. That's what I'm trying to find. Well, I know in a case like this, if he had gone the same distance on both legs of the trip, then I could just take a simple average. In this case, since he went 1/3 of the trip at 35 and 2/3 of the trip at 40, I could do 1/3 of 35 and 2/3 of 40 and find the answer. But I'm going to use some physics here. Since this isn't an acceleration problem or anything like that, it's just an average speed problem, I'm going to go with velocity equals distance divided by time. And I can use that as long as there's no acceleration. So in the case of the first leg of the trip, if I solve that for t, I'll just say t1, that would equal d1 divided by v1. And that'll give me a time. So D1 is 100. And V1 is 35 meters per second. Oh, now I see a problem. My top units are in kilometers and my bottom units are in meters. So I could go over here and make everything in meters, and I could say that's 100 times the K means 1,000. So I could say 100 times 1,000, or 1 times 10 to the 5th meters. So over here I can say 1 times 10 to the 5th meters divided by 35 meters per second. Look what's going to happen to the units there. The meters are going to divide out, and what I'm going to be left with is seconds over 1 over seconds in the bottom, which is the same thing as just seconds. So let's see, 100 times 1,000. Okay, and I get 2.85 times 10 to the 3rd. Seconds. Okay, now probably nobody would, say that many seconds. So if we divided that by 60, we would have, how many minutes that is. It'd be 47 minutes. They didn't ask us for that in the thing, but I'll just say approximately equal to 47 minutes. Okay, so then we've got T2 is equal to D2 divided by V2. Now again, we've got to check on those units. This time it's going to be 2 times 10 to the 5th meters, because originally they told us 200 kilometers, and that's going to be divided by 40 meters per second. So if I do that on the calculator, I get 5,000. So let's see, 5,000 seconds. Which is the same, if I divide that by 60, that's 83 minutes. Okay, now they asked for the total time. So, or the average velocity, I mean. The average velocity, the total average velocity would be the total distance divided by the total time. Well, I figured out time 1 and time 2, so I have that now. My total distance was the 300, so if I just write 300 kilometers, actually I should probably write it in meters, so that'll be 3 times 10 to the 5th meters divided by the 2 times T1 plus T2. That's going to equal, let's see, on the calculator, 2.85 times 10 to the 3rd plus 5,000 equals 7,850 seconds. So 3 times 10 to the 5th divided by 7,850 equals 38.2. meters per second. Okay, so now is that something that's reasonable? Well, let's see, we were doing the first leg of the trip at 35, and then the second leg at 40, So I would expect our average speed to be somewhere in between there. If you went half and half, it would be exactly between those two numbers, right? But since more of the journey was done at the 40 kilometers per hour, the number is probably going to be closer to 40, and it is. So that's how I would solve that problem. When we're doing a physics problem, we want to show the diagram, show the given information, show an equation that's been used. We want to label all of our numbers. And why we do that is because your work isn't just an attempt to find the answer, but it's a roadmap to how you found the answer. And that way, when I'm judging your work, I can look at it, and if you made a simple mathematic mistake, I can overlook that. I'm more interested in the physics. How did you solve it? From a professional standpoint, if another physicist is doing a problem, we need to know how they did it. What equations did they use? What assumptions were made? Did they make an assumption that they shouldn't have? So the more somebody can explain their work, the better off we are. So there's different types of, or better way to say it is velocity is different than speed, because velocity is a vector. Average velocity, though, or average speed, is an average of how fast you are going. If I said my average speed on the way to grandma's was 60 miles per hour, likely I didn't go 60 the entire time. As I left the driveway and drove through the neighborhood, I was probably going 25. And then when I got out on the interstate, I was probably going 75. But the average of that whole thing is just going to be a number that if you started at the beginning, went that speed the whole time, you would get there in the same time that you did with all those variations in speed. It summarizes the entire trip. However, when we're doing instantaneous velocity, which is the other type, we're talking about how fast were you going at a specific instant. So when you were going down the interstate, maybe it was 75. You look at your speedometer, that would tell you what your speed was at that particular instant. Or when the police officer aims the radar gun at you, that's going to be the instant that you were going. And this is why calculus is so helpful. Finding that specific point on a curve and being able to determine the slope of that can tell us all kinds of things about, distance versus time would give us velocity, and velocity versus time would give us acceleration. So using those in our knowledge of calculus, we can really refine stuff. Okay, acceleration. Acceleration is defined as a change in velocity over time. So Vf minus Vi over t. Now remember, that can mean speeding up, it can mean slowing down, but since velocity also has a direction associated with it, it can also mean changing direction. So acceleration can be any of those things. Sometimes you'll see the delta t here, your start time minus your end time. Your end time minus your start time, just like this. I'm just saying, the time elapsed during the process there. So either hitting the gas or hitting the brake counts as acceleration, but also using the steering wheel. The units are going to be meters per second squared, so when we see meters per second squared, we'll know we're dealing with an acceleration. Or more generally, a distance divided by a time squared, or 2 time units, would be an acceleration. So we're going to use that linear motion equation. We're going to assume, especially in this chapter when we're just learning how to do it, that the acceleration is constant. The acceleration is not going up and down. In real life, it will be. And we can account for that, we can handle that. Let's just learn it making the assumption that the acceleration is constant. We're going to use vector quantities, not scalar quantities. And we're going to always use the instantaneous velocities, not the average velocities, unless specifically told to use or find the average. The direction of the vector is indicated by the sign. If you screw the sign up, you're going to screw the vector up and you're going to get the wrong answer. All right, here's a practice problem that we're dealing with. So let's see how we do that one. So in this problem, we can see here I have highlighted the different important numbers that were in the thing. with the units after them. So meters per second, we can tell that's a velocity. Meters per second squared, we can tell that's an acceleration. Seconds, we know that that's a time. So given all those things, let's write down what we know. Okay, our time is 3.8 seconds. Our velocity initial is 15 meters per second. Again, the book might say VO for that, VO in the X direction, but I'm just going to label it VI. A is 5 meters per second. And VF is what we're looking for because it says how fast is it going at the end of the acceleration. All right, so let's think. If we're looking for VF, one formula I have is VF equals whatever our initial velocity was plus acceleration times time. It looks like I have all the information there to do that, so that's what I'm going to do. Now I'm going to start subbing in VI being 15 meters per second. Okay, I'm going to add that to 5 meters per second squared times 3.8 seconds. Okay, now if you look at the units here, if I've got seconds squared in the bottom and I got seconds here, this becomes meters per second. This also is meters per second. So together, I'm just adding 2 meters per second, and that's going to be a speed. Final velocity would be a speed, so that's what I want. And if I add those together, I get 34. So the thing would be going 34 meters per second, which is pretty fast, at the end of that acceleration. Practice problem number 2 here, we have a penguin sliding down a glacier from rest. And they're going to ask us how long does it take to get to the bottom. So let's take a look at how we would solve that one. In this problem, I'm going to write down what I know, and then I'm going to see what I can do to solve it. So we've got a code word here, at rest. When a penguin slides down the glacier starting from rest, that would mean that VI, let's see, get my right tool here. That would mean, there we go, VI, initial velocity is 0. Then it starts accelerating at a constant rate of 7.6 meters per second squared. I'm not sure it would really accelerate at a constant rate, but it makes the math a lot easier as we're learning this stuff. If it reaches the bottom of the hill going 15 meters per second, well, there's another velocity, and this would be our final velocity, would be 15 meters per second. How long does it take to get to the bottom? So I believe they're looking for a time. Time equals question mark. Well, from our definition of the acceleration, A equals VF minus VI, a change in speed over time. It looks like all the things I have over here would work in this equation. So I'm going to do a little algebra, rearrange it for t, which is just VF minus VI divided by A. Make sure all my units match. I've got meters per second, and 0 could be anything, so meters per second would be fine. So now I just do some math here. 15 minus 0 should label up. It's easy to get a little bit sloppy because you are in a hurry, but should really label everything. Meters per second squared. Okay, so now if I take meters per second in the top and I divide by meters per second squared, I'm just going to be left with inverted seconds on the bottom. which is the same thing as just plain old seconds. So I end up with t equals 1.97 seconds. Okay, and if you want to go back and look at that video about how many decimals and how many sig figs we should really expect in this, that's too many because we don't have that type of accuracy with the 7.6 number. That being the case, you know, right around 2 seconds is what it's going to take the penguin to slide down the hill. In this problem, okay, so now we're looking at our equations for displacement. Since we have the relationship v equals d divided by t, our average velocity is going to be our distance divided by our time. And we also, you know, could rearrange that for distance equals the average velocity times time. Could we say that, you know, our average velocity would be half of our two velocities? Yeah, we could say that. Well, what if we took this average velocity and substituted it into our second equation here? Then we have a nice equation for getting the distance that doesn't require the acceleration. Distance equals 1/2 vi plus vf times t. So let's see how we could use that. Here's a couple of practice problems for us. Okay, here's a pair of problems that are related. The first one says a car slows down from 45 meters per second to 30 meters per second. So let me just start writing what I know. My initial velocity was 45 meters per second. My final velocity is 30 meters per second. My time is 6.2 seconds. And I'm looking for a distance. Don't know that. Well, check to make all my units are the same. We've got meters and seconds, so that looks good. Let's see. Now I know there's a formula because I read the chapter. D equals VOT plus 1/2 AT squared. That's one way to look at this. The problem is we don't have the A. So what's a way that we could find the A? Well, if we take VI plus VF and we take half of that, that would be our average, and then we multiply it by our time. If we have average speed divided by time, that's going to give us our distance. So this would be a formula that we could use on this one. Let's see what we've got. D equals 1/2. VI is 45. Now in this case it doesn't matter if you switch them around because they're just added together. But in some cases, you know, it'll matter if you get VF in the wrong place or VI in the right place or what have you. But 45 plus 30 meters per second. Let's do our unit analysis too as we go here. 6.2 seconds. Let's see, this is going to be meters per second times seconds. So the seconds in the bottom are going to go away, and I'll just have meters and half of meters. Well, gosh, that's a way to measure distance, so we must be on the right track. And when we type that in the calculator, I get 232.5 meters. Okay, now the second one down here is cyclist speeds up from 8.4 meter per second pace. So that's my VI in this case. So I'll say VI equals 8.45 meters per second. And as he accelerates, okay, so he's accelerating, oops, that should be an A. I don't know what that is. He goes from 325 meters, that's D, 325 meters, in 30 seconds. Now, let's see, that should be T, not S. T equals 30 seconds. All right, let's see. We don't know what the A is in this case either. So that first formula I threw up there, that won't work, but this one works just fine. So let me write the formula down again, because I'm going to manipulate it. And it's always good when you're doing your homework to show me what equation you started with and what you did to it so that I can follow where you're at. Okay, we want to solve this because we're looking for his final velocity. And I should down here put VF equals question mark. I'm going to cross this out because I'm really not looking for that. I can find it, but I'm not looking for it right now. Okay, so I'm going to solve this thing for VF. Well, how to do that is I'm going to move the 2 over there, so I'll get 2D. And then I'm going to divide by the t. Maybe not do too many steps all at once. I get VI plus VF. Okay, if I want to get rid of the VI, I'm going to subtract it. So if I say 2D divided by t minus VI equals VF, let's do a unit analysis on this as we're looking at it. This would be meters per second. Up on the top we've got meters, on the bottoms we have seconds. This would be meters per second. So I'm going to end up with meters per second as my units. So let's see, 2 times 325 meters and 30 seconds. Then I'm going to minus 8.45, and I ended up with 13.2 meters per second. Now, the problem says that he's speeding up from this pace, so if I got a number lower than that, I'd question whether I did it right. 13's higher, it's really fast paced, so it makes sense. Okay, that'll be the end of our part 1 video. Next time we're going to look at equations that don't require VF. See you then.